Next property is very important and very interesting. Before jumping into that, let's go through some scenarios. Okay. So, first scenario is that I am running in air just like this. Okay. I am going very fast. Right. I will be able to go fast. Now, imagine the same situation. In that case, only one difference that I am inside a swimming pool. Water is up to this level. And I tries to go in the same fast manner which I was going through when I was running in the air. You know that I won't be able to go as fast how I was doing in the air, right? Because water will be offering some resistance, because of that I won't be able to go faster. So from that we can understand that there is some force is exerting by water on me than when I was running in the case of air. So what could be the reason? Is it density? That could be a possibility. Let's check that. In order to check that, I am taking you to another scenario, okay, where I am having two big beaker containing, this is water, here I am having coconut oil. Okay, this water, we can take the density of water as 1000 kilogram per meter cube. Here coconut oil can be taken as having a density of 900 kilogram per meter cube. Alright. Now, I am placing a metallic ball on top of it with a support. Okay. Now, at the same instant, I am releasing them. Then you will notice that in the case of water, the metallic ball went very quickly, but in the case of coconut oil, that went little slower than that in the case of water. Here you can see that water is having higher density than that of oil, but still the resistance offered by oil is higher than that of water. Am I correct? Yes. So it is not density. There is some other property which is causing this resistance. Let's understand that. You know that when a solid body is in contact with the surface, in order to move it, I have to exert some force, right? But there exists a frictional force between this body and this surface. As a result, I have to exert more force in order to overcome that frictional force. Then only I will be able to move that object. Similar way, there exists some frictional force between the liquids also. Let's see a case here. So, water is flowing between two metallic plates. So, some solid plate. Water is up to this level only, H2O. This is flowing in this direction. Okay. On top of water, I am having oil. Oil is moving, take water be at rest. Okay, water is at rest. Oil is moving in that direction. So, just like how the solid body was experiencing a frictional force, oil also will experience a frictional force in the direction opposite to its motion. Correct? So, there exists some internal resistance. That is in the case of oil and water. Now, let's take another case where between two plates, water is flowing. Okay, water is flowing. So, you will expect that there is no resistance will be there, right? Because oil is not there. There is no another layer is there. But in reality, all the fluids will be moving in minute small layers. Even though we see this entire water is moving as one unit, in reality, this is composed of so many very small layers. Okay, so water will be moving in this direction. Okay, so as a result, since water is moving in small layers, the bottommost layer will be offering a resistance towards opposite direction. This one will be offering a resistance for its adjacent layer. So there exists an internal resistance between the layers of fluid. This internal resistance is called viscosity. What it is called? Viscosity. The resistance force offered by resistance force offered by adjacent fluids of liquid is called viscosity or viscous force. Alright. In the case of metallic ball, when we drop in water and oil, it experiences some force, right? That is not called as viscosity, but that force is called drag force. The force experienced by a solid body when it moves through a liquid is called drag force. Drag force is not viscosity, there is a difference, but drag force is partially proportional to viscosity of the fluid in which the solid is moving. Alright, it's partly proportional, but just understand it is proportional. So, what is viscosity? The internal resistance offered by adjacent layers of fluid is called viscosity. And here we have seen that water is offering some different resistance, coconut oil is offering some different resistance, and air was offering some different resistance. So, this property has to be quantified. That means this is different for different fluids, right? So, this has to be quantified. So, let's do the quantification or making an expression for finding the viscosity for any liquid, any fluid. Consider that we are having two parallel plates, two very big parallel plates, and the bottom plate is fixed and we are having a top plate. Okay. Now, water is there in between the layers. Now, what I am doing is that I am applying some force F. You know that this is acting as a shear force, that is for sure, right? Because it is shearing that water. Now, you can see that because of the applied shear force, how the water will be reacting? It will deform continuously. This is what we have seen when we started the topic, right? In the case of fluid, when the shear force is applied, the fluid will be deforming continuously until the force is removed. In the case of solid, the solid will deform to an extent, then it will stop by offering a resistance force, right? But in the case of fluid, it will keep on deforming. So, we can find that in the case of fluid, deformation rate d theta by dt was more important. In the case of solids, d theta, the deformation was more important, but in the case of fluid, rate of deformation, that's how we will be quantifying the deformation, rate of deformation. So, let's note that. So, when this force is applied, it was here initially, a layer is shifted to this layer after a time dt. So, this angle is nothing but d theta. So, after a time dt, it has moved through a distance or an angle d theta. So, the top layer was moving with a velocity du, a small velocity du. So, during the time dt, how much distance it might have moved? Can you tell me? You know that velocity is nothing but distance by time, right? So, if we want to quantify the distance, it is nothing but velocity times the time. Velocity times time. So, if it was moving with a velocity du, the distance it is covered is nothing but du times dt. Fine. Now, in order for a perfect representation, the better term to use is shear stress. Shear stress is nothing but shear force per unit area. So, there exists some area of the contact, right? So, that area is nothing but area. So, instead of force, I will be using shear stress. So, that by multiplying with area, I will be able to expand or scale it up to any area. Okay. So, shear force is acting and as a result, it is deformed through an angle d theta. And after time dt, the layer is moved from this distance to this distance, that is nothing but du dt. Up to this, everything is clear, right? Perfect. Now, one important thing I can tell you is that if I am applying more shear stress, what will happen? Within a given dt, it will go to more deformation, right? That means if I am applying slight force, the rate of deformation will be lesser. If I am applying more force, what will happen? The rate of deformation will be more. So, I can straight away say that shear force is proportional to rate of deformation, right? Shear force is proportional to rate of deformation. This is called Newton's law of viscosity, just to give an idea, okay? The new name is not that much important here, just understand that the shear force applied is proportional to rate of deformation. Now, higher the shear force, more will be the rate of deformation, as simple as that. Let that be there. Now, from here, again I am coming back to here, from here I can write that tan d theta is equal to opposite side by adjacent side. Okay, I didn't define the adjacent side, let this distance be dy. It was a small distance dy. So, tan d theta is nothing but du dt divided by dy. Okay. Now, one important conclusion comes, that is, Even though we are showing this d theta in an enlarged manner, this d theta is very less. So tan d theta is nothing but d theta itself. That is the property of tan. So I'll be able to write d theta is equal to du dt divided by dy. Fine. From there, I can rearrange and write this equation as d theta by dt is equal to du by dy. This is very important finding. Why? Why? Because here we got shear stress is proportional to rate of shear strain, right? Now I am getting that rate of shear strain is equal to du by dy. What is du by dy? Du by dy is called as velocity gradient. How the velocity is changing with respect to y-axis. It will be having some more meaning as we go progress, but just understand that du by dy is called velocity gradient. So now I can rewrite this equation as tau is equal to, so directly proportional to du by dy. Now also that is not in the form of equation. In order to make that in the form of equation, I will be introducing a proportionality constant. So I got that tau is directly proportional to du by dy, or I can write tau is equal to mu into du by dy. Also I can write tau is equal to mu into d theta by dt. Everything is correct, right? Fine. This equation is very important. Tau is equal to mu into du by dy. This is also equal to mu into d theta by dt. As of now, mu is nothing but a proportionality constant. It is not having any physical significance, right? So let's try to understand what is the physical significance of this mu. So we got that tau is equal to mu into d theta by dt. From here I can write that mu is equal to tau by d theta by dt. So from here what I can infer? What I can infer is that mu is equal to tau by d theta by dt. So from that what I can infer is that mu is that shear force which is responsible for creating unit strain rate. In order to create unit strain rate, how much shear force is required? That is called mu, right? When d theta by dt is equal to 1, you will be getting mu is equal to tau, right? So we can say that mu is that shear force which is required to produce unit strain rate, correct? Now consider that there is a fluid whose mu is higher than, say it is having mu u2, viscosity is equal to, or mu is equal to mu2, which is greater than for that of initial fluid. From that what we can infer is that the shear force required to produce unit strain rate for the fluid 2 is higher than that of fluid 1. That means in order to produce the same deformation, I have to induce more shear stress, then only it will deform. Alright, then I can straight away say that in the case of oil, I was required more force, then only it moved. That's why it moved slowly, right? So oil will be having higher viscosity or higher mu than that of water, or water will be having higher mu than that of air. Okay, so mu is a quantity that is signifying the resistance force, the internal resistance force that exists between the adjacent layers of fluid. So this mu is called, what is it? Mu is called dynamic viscosity or coefficient of viscosity, like that. Okay, so mu is very important quantity. Mu is called dynamic viscosity or coefficient of viscosity, and it is characterized by the equation tau is equal to mu into du by dy. Alright, and we will be having so many problems from this area. That is going to be very much interesting also. So we have seen that shear stress can be expressed as mu into du by dy. We understood what is mu also, that is nothing but dynamic viscosity or coefficient of viscosity, right? So that is a term which is representing the quantity viscosity of a fluid. That also we understood. Tau is nothing but the shear force required to produce the velocity gradient du by dy or the strain rate d theta by dt, right? But let's have a proper understanding of this du by dy. Alright. Now consider that a fluid is flowing on top of a flat plate which is at rest. Okay, so the fluid is flowing. So I have already told you that fluid will be flowing in the form of small layers, right? So very small layers will be there. Small layers will be there. I am exaggerating and drawing in different layers. But the average velocity of this flow is given by something, say 100 meter per second. This is very huge. Just for understanding, I am giving some value. That's all. Now, what will be the velocity of the bottommost layer? According to no slip condition, the layer which is in contact with the solid surface will be having the same velocity as that of the solid boundary. In this case, this boundary, the plate is stationary. So what will be the velocity of the layer which is adjacent to that plate? Zero velocity, right? So as a result, this layer will be offering a resistance force to its adjacent layer, and because of that, that won't be going at 100 meter per second, and this will be going, say, at 2 meter per second. This layer will be offering a resistance, say this velocity is in this direction, right? So this layer is giving a resistance in this direction, this layer like this. So you can see that as we go along the y direction, the velocity is increasing, and after certain time, velocity is not changing with respect to y. So we can see a velocity profile, the velocity which is changing with respect to y axis, that is given by this du by dy. How the velocity is changing or the velocity profile. So if I am marking that, say this is, let's say this is y axis, this is the change in velocity. Okay. This velocity profile can take any shape. Say this can take a shape like this, or it can take a shape like this. But one interesting phenomenon happen, or interesting thing happen when it follows a linear relationship. What do you mean by linear relationship? So it just follows a single a curve which is of a constant slope. That is nothing but a line. A slope which is a line which is having the constant slope throughout. A curve which is at constant slope is called a line. So when this velocity profile is following a linear relationship, we will be having a line like this. Okay. In that case, I will be able to replace this du by dy by just u by v. Let's see, u by y. That is the distance from which it is happening. Let's see how we can do that. Say we are having 10 meters. Okay. Just for the sake of understanding, I am taking 10 meter. At 10 meter height, say this is 10 meter. 10 meter is very huge. Okay. Just for the sake of discussion, I am telling you. At that height, we are having a velocity of 100 meter per second. Okay. You know that at the boundary, we are having 0 meter per second. Well, that is at 0 level. At 50 or 5 meter, you will be having 50 meter per second. Okay. 50 meter per second. Let me mark it properly. Okay. Now, if you are taking the du by dy, what is the value coming for entire this thing? So, du by dy is nothing but 100 minus 0 divided by 10 minus 0. This is going to be 100 by 10. That is nothing but 10 itself. Now, just find du by dy for this part alone. So, what will be that? That is nothing but 100 minus 50 divided by 10 minus 5. Again, that is coming to be 10 meter per second. 10. Okay. Now, just find what is u by v or u by y at that point. Any point you take. Say at this point at 5 meter. Then you will be getting 50 by 5. That is also 10. So, that's why I was telling you, if the profile is linear, I can replace du by dy by just u by y, and thereby the equation will become tau is equal to mu into u by y. This is for a profile which is linear. Okay. So, that is very important. That's a special case of that. And many of the time you will get a numerical problem from this section. So in this section, if they are not mentioning anything about the velocity profile of du by dy, you can assume the profile is following a linear pattern, and you can take du by dy as u by y or u by h according to that problem. You will see some problem at that time, you will get a clarity about it. Okay, and we can modify this equation. You know that shear stress is nothing but shear force per unit area, right? So let me write that in term, then I will be having F by A. If I am taking this F here, I will be getting, A here, I will be getting mu A U by Y. Sometimes people say that mu A V by Y. So that sometimes some people find it easier to remember in that way. So it is something like this. So using this relation, we will be able to solve some problems. It's really going to be very interesting thing. Okay, I'm having beautiful problems from this section. You're really going to enjoy. Okay, so that is about viscosity and Newton's law of viscosity and the equation tau is equal to mu into u by y. All right. Now it's a time to understand how the viscosity of the fluid will be changing with respect to temperature. So in order to understand how the viscosity of a fluid changes with temperature, we should know what is the cause of viscosity. Okay, we are having fluid. There are two types of fluid, right? Gases and liquids. In both the fluids, the mechanism or the reason for viscosity is different. In the case of liquids, the reason for viscosity is because of cohesive force between the molecules. What do you mean by cohesive force? So we know that water is composed of so many water molecules, right? So between them, there will be some attractive force. This attractive force between same type of molecules is called cohesive force. So when we are talking about cohesive force, we should talk about the other part, that is called adhesive force. What do you mean by adhesive force? The force of attraction between molecules of two different types is called adhesive force. When you are pouring some water into a glass tube, then there exists some adhesive force between this glass tube and the water. That is called adhesive force. And inside the liquid, there exists cohesive force. So this change in, or which one is higher? Say adhesive force is higher than that of cohesive force, or cohesive force is higher than that of adhesive force. This will introduce some new level of properties, or one single property that we will see later. Anyway, I'll give you a clue. It is about surface tension. But anyway, right now our focus is on viscosity, how the viscosity is changing with respect to temperature, right? When I went to that, automatically I talk about viscosity, surface tension. But coming back to the point, what is the reason for viscosity in liquid is because of the cohesive force. Because of the cohesive force, each of the molecule will be attracting each other. As a result, the flow won't be as smooth as if there is no viscous effect is there. So it will be attracting, right? So it will be stopping the flow. That's all you have to understand. In the case of gases, the reason is entirely different. It is not because of the cohesive force. Why? The cohesive force in the case of gases are very negligible. Why? Because in the case of gases, molecules are placed very at large distance compared to liquids. As a result, there is no proper attractive force within them. So viscosity due to cohesive force in gases are negligible. Then who is causing the viscosity in gases? That is because of the molecular collisions. You know that in gases, molecules will be colliding each other, right? Okay, because of the collision, they are not able to flow, or there exists the resistance to the layer of gases. We can say like that. Just imagine that you are going in a highway which is having a lot of traffic blocks. So many collisions will be there, right? As a result, you won't be able to go. Just imagine that way. So in the case of liquid, the viscous effect is due to cohesive force. In the case of gases, viscous effect is due to molecular collisions. Now coming back to the basic question, how the viscosity of fluid is changing with respect to temperature. As far as liquid is concerned, when the temperature is increased, the cohesive force is decreasing. As a result, the cohesive force weakens. Then that is the reason which because of that we are getting viscosity, right? So when temperature increases, viscosity of the liquid will decrease. So I'll write temperature increases, mu will be decreasing. Okay. Now that is for liquid. What about gases? When temperature increases, mu, what will happen to the viscous effect of gases? You know that when temperature increases, the collision inside the gases will be increasing, right? Because each molecule will be having more energy, so they started to collide each other. It is kind of a traffic junction where there is no traffic police or a traffic light. What will happen? Everybody will be going here and there. Finally, a big traffic jam will be occurring, right? As a result, your vehicle won't be able to move from one point to other point. So finally, it is equivalent to say that flow is restricted. So as the temperature increases, traffic jam. So viscous effect is decreasing. Okay? Viscous effect is increasing. So when the temperature is increased in gases, viscosity will be increasing. So we can plot a small graph like this, mu versus temperature. So this will be the plot for liquid, this will be the plot for gases. Alright. This is how viscosity will be changing with respect to temperature for liquid and gases. Alright. We have seen that tau is equal to mu into du by dy, right? But we never talked about what is a unit of the dynamic viscosity. Let's find the unit. So from here I can write mu is equal to tau by du by dy. Tau is nothing but shear stress, that is having a unit of force per unit area, that is Newton per meter square, whole divided by velocity. Change in velocity will be having the same unit as velocity, that is meter per second, then divided by meter itself, because it is length, right? So as a result, this meter cancels out. We will be getting Newton second per meter square. What is Newton per meter square? Pascal, right? That is a unit of pressure, so we will be getting Pascal second. Oh, this is also equal to kilogram per meter second. So these are all the three units of dynamic viscosity in SI units. Okay. Similarly, we will be having unit in CGI unit also, because this unit is in most of the time in the questions you will be finding the unit in CG unit for viscosity. That is given as poise. 1 poise is equal to, just understand that this is very important, 1 poise is equal to 10 raised to minus 1 Newton second per meter square. This relation you should be finding, remembering. Most of the time you will be getting some problem related to water. So they will say that at 20 degrees Celsius, viscosity or dynamic viscosity of water is 1 centipoise. So 1 poise is equal to 10 raised to minus 1 Newton second per meter square, right? And we have seen that viscosity of water at 20 degrees Celsius is equal to 1 centipoise. So you know that centi means 10 raised to minus 2. So 1 centipoise means 10 raised to minus 2 into 10 raised to minus 1 Newton second per meter square or Pascal second. So it is nothing but 10 raised to minus 3 Newton second per meter square. This is the viscosity of water at 20 degrees Celsius. So on similar ground, we can say that viscosity of mercury, that is almost similar to viscosity of water. Interesting, right? We know that density of mercury is 13,600, whereas density of water is only 1,000. But still, their viscosity is very near. Water is having 1 centipoise, at the same time, mercury is having 1.55 centipoise at 20 degrees Celsius. Very near, right? So these things clearly distinct that there is a distinct distinction between density and viscosity. Fine. Now, Newtonian fluid and non-Newtonian fluid. We have seen that shear stress is proportional to d theta by dt, or shear stress is proportional to velocity gradient du by dt, right? This is how fluid were behaving, right? That's how we started. But in reality, not all the fluid follow this law. So some of the fluid is having some exception. We will come to that. So those fluid which follows this law, that is shear stress directly proportional to shear strain, are called Newtonian fluid. Those fluid which will not follow this rule is called non-Newtonian fluid. Anyway, regarding Newtonian fluid, we have already learned enough. We have seen the expressions also. Now, the most important term now for us to learn is what are non-Newtonian fluid, how it is different from Newtonian fluid. Let's see that. So, we have seen that in the case of Newtonian fluids, shear stress is directly proportional to strain rate, right? Or shear stress is directly proportional to velocity gradient. But in the case of non-Newtonian fluid, it is different. In the case of, there are different types of non-Newtonian fluids are there. For example, in the first case, shear thickening fluid, where we will see that as we keep on increasing the shear stress, the resistance offered by them is going to increase. That means it is going to, we will feel that when if we keep on doing the shearing, and when we increase the shear force, we will see that this is offering more resistance. That is called shear thickening. At the same time, we will see that some fluid will behave the opposite way. We will keep on shearing, then we will see that initially it was difficult to shear, but as we increase the force, it started to behave very nicely, so that we will be able to shear very easily. Those things are called shear thinning fluid. Anyway, how to represent them? What are their specific names? I'll give them a note. So, non-Newtonian fluids can be represented mathematically as like this. Tau is equal to A into du by dy whole raised to n plus b. This is the standard way of representing non-Newtonian fluid. And in one of the first case, or the first case for non-Newtonian fluid is dilatant fluid. What are dilatant fluid? Dilatant fluids are shear thickening fluid. So, where as we keep on increasing this applied shear force, this particular solution start to thicken. That will be offering more resistance to applied shear force. So, for those things, I can rewrite this equation as tau is equal to A into du by dy whole raised to n, for which b is equal to 0, and this n is greater than 0. So, how I can rewrite this? This is going to be A into du by dy whole raised to n minus 1 into du by dy. Both are same, right? Both are same. Now, what will we do is that we will call this particular expression as apparent viscosity. What we call it as apparent viscosity. So, I will be able to express this as tau is equal to A into du by dy whole raised to n minus 1 into du by dy, right? And this is called mu apparent. So, I can write this as tau mu apparent into du by dy. Okay. This is how we will be representing dilatant. This is how we will be representing dilatant fluid. Alright. Now, you can see that in the case of dilatant fluid, as this n is greater than 1, we can see that this will keep on increasing when we are increasing shear force. So, it will offer more resistance. Example for dilatant fluid is starch solution. It will be behaving like that. Or you can take corn powder and you can mix it with water and you can see yourself how it is behaving. Alright? Okay. That's about dilatant fluid. How we can represent on a graph? Let's see that. So, if you are going for tau here and du by dy here, it will be going like this. A curve with increasing slope. That's how we will be representing dilatant fluid. Next one is, can you tell me what is the next one? Dilatant fluid is the one in which apparent viscosity will be increasing as we increase the shear force, right? The other one is reverse of that. This is called shear thinning fluid. What is it called? Shear thinning fluid. In that case, as we apply shear force, as we increase the shear force, it will offer less and less resistance. Take the case of paint. Okay, if you do like this, take a paint can, and if you do like this, initially it will be difficult to do it. But as we keep on increasing the force, what will happen? It will be easier to do this. That means as we increase the shear force, it is offering less and less resistance to that. That is the case of shear thinning. So next one is shear thinning or pseudoplastic. How to represent them? Tau is equal to mu apparent into du by dy, or tau is equal to A into du by dy whole raised to n minus 1 into du by dy. Just like how we represented dilatant fluid itself, but the difference is that here n is less than 1. So as I told you, take the case of paint. As we increase the shear force, it will be offering less and less resistance. So how to represent that on a diagram? Tau du by dy diagram. This is a case in which it will be keep on decreasing. Okay. So this is how we will be representing pseudoplastic. Okay, fine. Now we are having one more special case, that is Bingham fluid. They are called Bingham fluid. Okay, what is Bingham fluid? In the case of Bingham fluid, it is a bit interesting thing. How it is interesting? Every day you are using toothpaste, right? So when the toothpaste is inside that tube, it is not, if it was water, consider that the water is inside the tube. When the moment we open that and if we keep on the table like this, water will come out, right? But in the case of toothpaste, it won't come like that. Until and unless I apply some force, it won't come. So that case, what is happening? Let's try to draw the tau du by dy diagram. So in the case of fluid, how we define fluid? Fluid is a substance that will be continuously deformed even under the very small shear force, right? But in the case of Bingham fluid or in the case of toothpaste, for some time it resists. Okay, for some time it resists the applied shear force, then it flows like a fluid. So when we apply pressure or when we shear it, what is happening? At that time only it comes out, right? So for some time it is acting like a solid, thereafter it is flowing. So at that time it is acting like a liquid. So that is a specialty of Bingham fluid. Example, first example is toothpaste itself. Second example is slurry. Okay, slurry is nothing but or sewage slurry, everything you can consider, they are also behaving in the same way. So these are all dilatant pseudoplastic Bingham fluid you have seen, alright. And let's see how we were representing them. This is how we represented dilatant fluid. This is how we will be representing, what is it? Decreasing slope, that is nothing but spheroplastic. This is nothing but Newtonian fluid. There is one more category, that is time dependent viscosity. It will be showing time dependent viscosity. Okay, see, there are some paints, or take the case of cement solution. Take the case of cement solution or gypsum solution. Okay, initially we mixed it, you will be able to do the shearing without any problem. But as time passes, it will become difficult and difficult. Even I am not changing the shear force, as time passes, it will be offering more resistance. So it is a time dependent viscosity it is showing, right? Similarly, you take the case of a lipstick or paint. Okay, so in that case, what is happening? Initially, it will be difficult, but in the case of lipstick, initially it will be difficult, but when we keep on doing it, it behaves like easily. We will be able to apply it very quickly. Alright. So they are all called thixotropic and rheopectic. Okay. So if I am representing shear force with respect to time, applied required shear force with respect to time, it will be like this. This is rheopectic. So other one is thixotropic. Alright. So thixotropic is a fluid in which resistance will be decreasing with respect to time. In the case of rheopectic, resistance will be increasing with respect to time. That is a example for rheopectic is cement solution, and example for thixotropic is nothing but lipstick. Alright. Okay, paint also you can consider. Okay. Now, one important example I forgot. We were talking about pseudoplastic, right? there are some paint which is having latex content in it. So what is the advantage? Advantage is that painting requires some condition. Okay, the moment when we drip brush into the paint bucket and when we take it out, it should not fall out. Okay, so it will not fall out if the paint is very thick, right? In a common layman language, I am telling. If it is very thick, it will not fall out. It will not drip. But if it is very thick, I know that it will be very difficult to paint also. But these latex based paints are very unique things. You know what is happening? It seems to be thick. When I drip my brush and when I take it out, it will be showing like it is very thick. But the moment I apply shear force on it, it will become very thin fluid. That means its viscosity is decreasing as I increase in the shear force. Initially applied shear force was less, so it was thick. But as I increase my shear force, it was easy for me to apply paint without any difficulty. But if it was thick itself, what would have happened? It would be very difficult for me to paint. If it would have thin, continuously it was showing the same viscosity, means the moment I take it out, paint started to dip. But it will be easier for me to paint. But this latex based paint is a unique thing wherein initially its viscosity is less, very high. As a result, it will not drip. Even some shear force is acting in the form of gravitational force, but it will not drip. But the moment I started to paint, the shear force is increased. At that time, it behaved like a very thin fluid. I will be able to paint very nicely. Interesting example, right? Alright. So these are all called non-Newtonian fluids. We have seen, what are the fluids we have seen? Dilatant fluid, that is where viscosity increases with the increasing applied shear stress. Then we have seen pseudoplastic. Just now we have seen the case of latex based paint where viscosity decreases with increasing shear stress. Then we have seen Bingham fluid where that fluid will be behaving like a solid for a certain time. After that, it behaves like a fluid. And slurry and toothpaste are example for Bingham fluid. Then we have seen time-dependent viscosity changes, that is thixotropic and rheopectic. In the case of rheopectic, viscosity increases with the time, that is in the case of cement solution. Initially it will be easy, but as time passes it settles down, right? So it will be offering more resistance. Then in the case of thixotropic, we are having the example of paint and lipstick, normal paint and lipstick. Okay, so how the paint is coming here? Initially, if you take the paint, it will be difficult to do the shearing. But as you keep on doing it, that means as time passes, you will be finding that it will become thinner and thinner. There is the resistance offered by is less. That means time dependent viscosity is shown, right? Okay, that's all about non-Newtonian fluid. Some examples also you have seen, that is sufficient. Now let's move on. There is something called ideal fluid. What is ideal fluid? Ideal fluid is a fluid which is completely incompressible and its viscosity is 0. So density change will be 0 and its viscosity is also 0. Actually, there is no such fluid in nature which is ideal fluid. If such fluid exists, almost all of our calculation would have been very easier. But then why we are defining a fluid with calling as ideal fluid? The reason is simple. In some places, we will be able to neglect the effect of viscosity. So at that case, we will be able to neglect and we can treat it as ideal fluid and we can do some of the calculation. In some places, we will be calling it as ideal flow. Okay, I will give you a brief, some idea that we will see later also. See, when a plate is there and air flow is coming, you must have heard about boundary layer theory, right? So it will form a boundary layer like this. Okay, but airflow is happening here also. Okay, these airflows are unaffected by this solid plate. So in this area, effect of viscosity will be null. So in that case, we can say that this is ideal flow. Here viscous effect is there. We cannot call it as viscous force here. So ideal flow and ideal fluid are different. Ideal fluid is a really ideal fluid. There is no such, in real life, there is no such fluid which is called ideal fluid, wherein density change is 0. Density change we can have 0. That is, you take any liquid where we can call it as incompressible because the change in density is very much negligible. But this, there is no such fluid with a viscous effect is 0. But for some cases, we will be able to take it. And another one is ideal flow. A flow in which viscous effects are negligible. That's why I gave you an example. When a fluid flows over a solid plate, a boundary layer develops, but on top of that, these effects are not affected. So this area we can call it as ideal flow. Anyway, you don't have to go into the depth of that. This is just for your own understanding. That's all. Nothing to do with exam as of now.